In Chapter 3 of Headfirst Design Patterns, we're going to talk about the decorator pattern. Let's look at the Starbuzz coffee application. This application is used for taking orders at Starbuzz Coffee and determining the cost of the order. When Starbuzz just started out, the application was simple. There were only 4 beverages: house blend, dark roast, decaf, and espresso. Each beverage had its own description, and each beverage had its own cost. But then someone came up with the revolutionary idea to add condiments to the beverages, like milk, mocha, soy, and so on. And the application developer had to figure out how to extend or modify this design so that it could handle those condiments. Here's one way to add the condiments without even changing the design. Just create a separate class for every possible combination of beverage plus condiment, and add it as a subclass of beverage. Fortunately, it quickly became obvious to the developer that this approach would not scale. So the developer settled on another approach. The developer used Boolean variables to keep track of the condiments that would be included with each beverage. The cost function of the abstract beverage class simply held costs for each condiment. Individual condiment costs were added to the total cost only if the Boolean for that particular condiment was set to true. The cost functions for the concrete classes overrode the cost function of the abstract beverage class in the following way. It called the superclass cost method to get the cost of all the condiments, then added its own cost, the cost for the base beverage, to the total. So this is the design. And in fact, there may be a few problems with this design. But before I tell you what the book says they are, please pause the video and see if you can find some potential problems. In particular, try to think of what requirements or factors might change and how those changes might impact this design. Ready? Here are some potential problems with this design as given by the book. First, price changes for condiments will certainly force us to alter existing code. If we double the price of milk, we have to change the cost method in the abstract class beverage. That's where the prices are kept. If we want to add a new condiment to this design, we'll be forced to alter the cost method in the superclass and add a new field and add a new has method. Another change is that we may decide to add new beverages. For some beverages, the condiments may not be appropriate, but a subclass like chai tea will still inherit methods like has whip. Finally, what if a customer wants a double mocha? There's only a Boolean variable saying whether the beverage has mocha or not. Here are the problems we just discussed laid out on their own slide. I'd like to focus on the second problem because I think this one is the most significant. It's likely that we'll want to add new condiments, and we really should not have to change existing code to do that. If you're forced to modify your code when you're simply extending your application, then you should probably reevaluate your design. This concern came up in the previous chapters for the strategy pattern and the observer pattern as well, but it's time we gave an explicit design principle here. This is known as the open-closed principle. Classes should be open for extension but closed for modification. It was proposed by Robert Martin in a paper on object-oriented design principles, and he called it the most important object-oriented design principle. Classes should be open for extension but closed for modification. But what does this exactly mean? Open for extension means that you should feel free to extend classes with new behavior if your needs and requirements change, as they certainly will. However, understand that someone spent a lot of time getting their code correct and bug-free, so they don't want you altering existing code. Naturally, your design has to be set up correctly for this principle to work. Obviously, the Starbuzz coffee application is not set up this way, because when we wanted to extend the application by adding new condiments, we were forced to modify existing code. To remedy this situation, we're going to use the decorator pattern. Here's an example of how the decorator pattern works. We take a dark roast object, which is one of our base beverages, and then we decorate it or wrap it with a mocha object. Now we have a beverage object that we might call dark roast with mocha. So we can decorate or wrap our dark roast with mocha object with a whip object. And we end up with a beverage that might be called dark roast with mocha and whip. The outermost decorator is the whip object. So if we want the cost of our beverage, we call the cost method of the whip object, which adds in the cost of the mocha decorator, which in turn adds in the cost of the dark roast. Let's look at a picture of this. Mocha wraps dark roast and whip wraps mocha. Suppose dark roast has a cost of $4 and mocha has a cost of 50 cents and whip also has a cost of 50 cents. For this to work, all of these objects must be beverages. That is, they must all inherit from the abstract beverage class. It seems a little odd since whip and mocha are condiments, not beverages. But if this helps, you can think of them as being named beverage with whip and beverage with mocha. When you call the cost method on the beverage with whip object, it calls through to the cost method of the beverage with mocha object, and it adds 50 cents to the result. The beverage with mocha object does the same thing. It calls through to the dark roast object, which is $4, and adds 50 cents to that. So the cost of the beverage with mocha object is $4.50. Therefore, the cost of the beverage with whip object, which also has mocha, is $5. The decorator pattern attaches additional functionality to an object dynamically. Decorators provide a flexible alternative to subclassing for extending functionality. Let's look at the new diagram for our Starbuzz coffee application, and I think this will be easier to understand. In this design, the abstract beverage class is still at the top of the hierarchy, and the four base beverages, house blend, dark roast, decaf, and espresso, are still subclasses of beverages. What's new here is that there's an abstract class named condiment decorator that inherits from beverage. The important thing about the condiment decorator is that all condiment decorators must have a field named beverage that has type beverage with a capital B. And you can see this when you look at all the concrete condiment decorators, milk, mocha, soy, and whip. They all have a beverage field. So the cost method for whip is simply going to return beverage.cost plus 50 cents or whatever the additional cost is, where beverage is the field. But keep in mind that even the condiment decorators are beverages, so condiment decorators can decorate or wrap both the base beverages, house blend, dark roast, decaf, and espresso, and they can also decorate or wrap other condiment objects, milk, mocha, soy, and whip. Here's the general structure of the decorator pattern. If you look at this diagram carefully, you should notice a difference between these decorators and the decorators in the Starbuzz coffee application we just looked at. I won't ask you to pause the video here, but if I give you 10 seconds, can you spot the interesting difference between these decorators and the decorators in the Starbuzz coffee application? 10 seconds starting now. Okay, the difference is that in these decorators, there is something new, something additional. Remember that the description of the decorator pattern said that the decorator pattern attaches additional functionality to an object dynamically. Here, concrete decorator A effectively adds a new behavior method to the wrapped object, and concrete decorator B effectively adds the field new state to the wrapped object. In the Starbuzz coffee application, the decorators, that is, the condiments, did not add any new behavior or any new state to their base beverages. Mind you, the design still turned out to be quite useful, but I just wanted to let you know that there's another level of usefulness with the decorator pattern that comes in the form of new behavior and/or new state. To show you a quick example of a decorator pattern that extends functionality, let's look at a real-world decorator pattern from the Java I/O library. Suppose you wanted to read a text file from the system, one line at a time, and you wanted to count the number of lines in the file as you read it in. File input stream is a base component that lets you read a file. Other base components in the Java I/O system include string buffer input stream and byte array input stream. Buffered input stream is a concrete decorator that adds behavior in two ways. First, it buffers the input, which improves performance. In addition, it allows you to read character-based input a line at a time. Finally, line number input stream is another decorator that allows you to count the number of lines as you read the data. Buffered input stream and line number input stream both extend filter input stream, which is an abstract decorator class. And that concludes our introduction to design patterns. In the next module, we'll go over more design patterns, but at a little faster pace. And we'll see how to combine multiple design patterns in a single application. I'll see you there.